name's Ian. I'm a postdoc at University of Warwick. Let me show you how to evaluate a tree. Today we're going to be talking about space. You've probably seen it before, maybe even worked with it yourself. Alongside time, it's one of the most fundamental resources you can study, whether it's algorithms, complexity, or if you really want to go there, even in practice. Space and time have been around since the beginning of the field, and from early on we've known a relationship between them. Any algorithm which uses space at most s can also take time that's at most 2 to the s. The most important instantiation of this for today is that L, the class of logarithmic space computable functions, is contained in P, the class of polynomial time computable functions. Now, while we've known that L is contained in P for ages, there hasn't been much to show in the other direction. We know that time t can be simulated with space a little less than t, but we're nowhere close to showing, for example, that p can be done with polylogarithmic or even n to the epsilon space. And that's for a pretty good reason. Most researchers don't believe it's even true. In some sense, it's similar to p versus np. If you prove a conditional result where the condition is, say, L is not equal to p, I'd say for most researchers that's as good as proving an unconditional. But perhaps unlike p versus np, the P versus L problem has felt much more tractable as of late. In fact, we have a concrete approach, one that promises to separate P from L, which has quickly picked up steam over the last 15 years. Today we're going to talk about this problem, the logic behind it, objections to this logic, and in the end we're going to show how to defeat it, and what such an algorithm tells us about space. Let's get started. On August 27, 2009, Steve Cook gave a talk at a workshop on barriers in computational complexity theory. In it, he talked about a paper that he had had with Pierre Mackenzie, Dustin Ware, Mark Braverman, and Rahul Santhanam about a problem which is clearly in P, but which they strongly conjecture is not in L. He gave some intuition as to why the problem should be hard and talked about a number of partial results. They called it the tree evaluation problem. TEP for short. To get a sense of their approach, let's talk about the relationship of L to another class, called NC1. Similar to L and P, NC1 is the standard of efficiency for a different model of complexity, namely formula depth. Again, we've known for a long time how to fit NC1 into the picture. NC1 is contained in L, which itself is contained in P. To see that NC1 is in L, consider the following algorithm for computing a log depth Boolean formula. We're going to compute the left child of the root, save its value, erase all the other work that we did, and then compute the right child. If you think about this recursively, the space that it will take to compute the whole formula is 1 bigger than the space it will take to compute the right child, assuming for simplicity that the tree is balanced. Now, the space that it will take to compute the right child is just an instance of computing a Boolean formula, but of height 1 less. So by the same logic, we can compute the left child, erase all the work except for saving the value from above, and the current value of the left child, and then we're going to compute the right child in the same way. And if you just move your way down to the leaves, you'll see that we'll end up storing 1 bit per layer of the tree, or log n space total. Okay, but what does this have to do with L versus P? Well, notice that the argument I gave is pretty tight. It relies on the tree that you're trying to simulate only having a logarithmic number of layers, and every time we put aside a value, it's only 1 bit. If you were to change either of these things, it's not clear at all how to get this thing into logarithmic space. Also, while I stated this is an algorithm, it's natural to assume that this is the best you can do. In particular, you're going to have to compute the output node of a formula, and to do so, you will have to compute both the left and the right child. And once you've done one of them, assuming you're not trying to do them in parallel, you will have to write down the answer and move on to an instance of height only 1 less. Cook et al. Decided to take advantage of this supposed lower bound to modify the problem in a way that it would stay in polynomial time, but would seemingly require a superlogarithmic amount of space. Concretely, we'll have a balanced binary tree of log depth, just like we did before, but now we'll start with log n bits per input instead of just 1. To make the evaluation work, we have to specify a whole function at each internal node,
a function taking two sets of log n bits, one from the left and one from the right, and spitting out log n bits for the next node. We'll take each of these functions, along with the values of all the leaf nodes, as part of the input, and our goal is to evaluate the tree from the ground up. Tree evaluation. Cook et al. Conjectured that any optimal algorithm for tree evaluation would have to remember log n values, that is, one for each layer of the tree, of log n bits each, giving us log squared n space in total.
And this idea for coming up with a hard function isn't completely new. In general, there's a framework in complexity where if you want to come up with a hard function, it sometimes suffices to compose a bunch of easy functions together. In fact, almost this exact same tree evaluation idea had appeared decades before the 2009 talk. The KRW conjecture, named after authors Maurizio Karchmer, Ramraz, and Avi Wigderson, states that a slight variant on TEP is hard for NC1. This KRW question is open after 35 years, with new works coming out all the time, and almost all of the work points to the idea that this function should be hard and not easy for Boolean formulas. The tree evaluation paper made an equally forceful argument for why this function should be hard for space. In fact, Steve Cook believed in it so much that in that 2009 talk, the very first one on the subject, he put $100 down for anyone who could beat the full lower bound, as conjectured by the compositional logic. Soon after this original paper, there were multiple follow-up works showing this full lower bound holds for increasingly strong models of space, not just in L, but also within NL. All this means that going into the 2020s, it was pretty clear that space hardness of composition was on the right track. So, that was the state of affairs. Right from the get-go, Cook was willing to stake what in graduate student terms is an entire month's grocery budget, plus a 6-pack of PBR, for any algorithm beating log squared space. Forget putting TEP in L entirely. But okay, I said that was going into the 2020s. Where are things now? Well,
in 1985, Amherst actor-comedian David Barrington released a result which stunned the theoretical computer science community. His result, which we now know as Barrington's theorem, states that NC1 can be computed by polynomial size, constant width, permutation of branching programs. For now, the story starts a few years later, with a follow-up work in 1989 by Michael Ben-Or and Richard Cleave. What they showed, in different language of course, is that some instances of tree evaluation are too structured to be hard. In particular, if every node in your tree computes modular arithmetic, that is, treat your log n bit numbers as elements in some poly-size ring, and every function either computes plus or times of its two inputs, then it turns out the entire instance is in logarithmic space. With reference to our compositional logic earlier, they show that you don't, in fact, need to remember one log n bit value for every layer in the tree. In fact, just remembering 3 values is enough to compute the entire function, plus a little bit of extra space to do some modular arithmetic, and to keep track of the runtime. And we'll return to that point in just a minute. Now, what I just said is a little bit misleading, because they don't get around storing one value per layer in the tree. In fact, they store many more values than that. But, and this is the crucial part, they don't store all these different values in different blocks of memory. How does that make any sense? Let's zoom in on one node and see what that might look like. In a typical scenario, we assume recursively that we can compute the values of the left and right children. However much memory this takes, we end up with one block holding the left child and one block holding the right child. We then put these together to get the value of our node and store it in some other part of memory. We can then erase the values of the children and move on. Ben-Or and Cleave took a similar approach, but via arithmetic. Remember that we're going to assume every node in our tree computes modular arithmetic over some ring. And so let's just chunk up our memory such that every block remembers one value from the ring. We were sort of implicitly doing this before. And now, instead of adding the values, in the sense of storing them in memory, we're literally going to add values to our memory, in the sense of arithmetic over the ring. If the memory we had before is blank, and we think of it as having the number 0, this is the same as before. We add the children to 2 parts of memory, compute the function at the current node, which again we're assuming is either plus or times,
into some third part of memory, subtract the children back out of the place where we put them in, and again, this is addition and subtraction being the arithmetic sense, and we've computed the node while resetting the two children spots.
Now the next step in the Benoring-Cleve construction is to ask a kind of crazy question. What happens if, instead of adding or subtracting to empty memory, i.e. memory that's set to 0, we add or subtract to memory that already has a value stored in it?
We're going to think of our memory as having 3 registers, say RL, RR, and RU, where we want to add the left, right, and current values respectively, which we'll call VL, VR, and VU. Only now, instead of thinking of these registers as holding 0, we're going to assume that they already have some ring elements stored in them. We'll call them tau L, tau R, and tau U respectively.
The question is, can we do this when the tau values aren't 0? Can we take a program PL, which adds VL to the register RL, which has some value tau L in it, and can we do the same with the program PR, adding VR to RR, which has tau R in it, and without ever directly looking at VL and VR, design a program PU, which computes the value VU and adds it to RU? Let's stop here and show that this is enough to prove their main theorem, that 3 values is enough to compute the entire tree.
At the bottom, we can easily have a program to add the value of a leaf node to any block of memory we want. This is just atomic since it's in the input itself. At each of the intermediate nodes, we apply the relevant program, where the left register RL is whatever we computed the left child into, the right register RR is wherever we computed the right child into, and the output register RU is whatever the third spot is. Rotating the roles of the 3 blocks of memory in this way, and letting tau L, tau R, and tau U be whatever's already sitting in them when we make a recursive call, we can compute our way up the tree, starting from the leaves until we finally reach the root node and get our final value, the value of the TEP instance itself. In honor of the technique used to prove this, Benoring-Cleve dubbed these recursive arithmetic operations register programs.
Now there are 2 loose ends to tie up. The first is that it doesn't really matter if you can compute this value VU if you end up messing up your memory in the in-between by adding a whole bunch of extra junk. To get around this, the programs we design are what were later dubbed clean register programs. A clean register program does exactly what it's supposed to do, which is add the value VU to the register RU, and does nothing else. The second thing is this time element that I mentioned earlier. This is a recursive program, which means every time we want to compute the value at U, we have to compute the values at L and R recursively.
An easy argument shows that asymptotically, our program runs in time c to the h, where c is the number of recursive calls we make to the layer below, and h is the height of the tree. And we know that h is log n by construction, meaning that we can only tolerate a constant number of recursive calls at each node before the program takes super polynomial time, and hence super logarithmic space.
This is exactly what Benoring-Cleve achieved. They show how to construct the program PU using only a constant number of recursive calls to both PL and PR, plus a few extra instructions. Thus, they end up with a program computing the entire tree evaluation instance of polynomial length, and thus putting it together with the working memory for the registers in logarithmic space. I spend all this time talking about the Benoring-Cleve result because, well, it's cool. And kind of mind-bending when you think about it. It shows how memory can be not just used, but reused, being made to store multiple values in memory at the same time, and simultaneously being a site of computation. This obviously flies in the face of the compositional logic we saw earlier, and to me at least, it says something pretty incredible about space. But it's especially relevant for today, because the technique they used ended up being the starting point of all the follow-up works, including the one that we're going to see today. First off was a result from 2014, a paper by Harry Berman, Richard Cleve, Michal Kutsky, Bruno Loff, and Florian Spielmann. They showed, in a slightly different setting, that a similar result holds for the majority function. If you can add all the input bits to a majority gate into memory, where now addition is again modulo a ring, then in a constant number of recursive calls, you can actually compute the majority function and add it somewhere else in memory. Since these register programs are about arithmetic, they relied on an algebraic characterization of the majority function, i.e. a polynomial representation of majority. The second paper I want to talk about is by Cook, no, not that one, yes, Cook and Mertz, your present authors. In 2020, we showed that the same sort of ideas can work not just for some structured polynomials, but arbitrary polynomials. And combining this with the idea of translating Boolean functions to polynomials meant that the conjecture about tree evaluation problem by Cook, yes, that one, and others was about ready to fall. I say about ready to because we didn't achieve anything near log space. From the conjectured lower bound of log squared n by Cook et al., we managed to achieve a log-log savings, log squared n over log-log n. That's a lot of logs. The barrier, and the reason I stressed it so much earlier, is the amount of recursion. We still show that you can store only 3 values over the field for an optimal logarithmic space algorithm in the register memory, but unlike before, where only a constant amount of recursion was needed, in order to compute a polynomial of degree d, we require recursion which is exponential in the degree.
The polynomials for tree evaluation end up having degree roughly log n, and so exponential is polynomial, and raising that again to the h gives you a runtime of n to the log n, or log squared n memory for short. And it takes some encoding tricks and degree balancing to make things work out.
And as we stated at the end of our paper, any improvement to the amount of recursion needed to compute a polynomial would be enough to get a savings in the space for tree evaluation. Which, finally, brings us to today, where we show that a linear amount of recursion is sufficient. We do have to make another small sacrifice, which is that we have to embed our original ring into a ring that's slightly larger. I'll get into the exact numbers in just a minute, but for now, a recap of what we've seen so far. Taking inspiration from Barrington's theorem, Benor and Cleve showed that you can compute arithmetic versions of tree evaluation problem while remembering only 3 values, not proportional to the number of layers in the tree. They do so by a different way of recursively computing values in the tree. Berman et al. Used this same technique, but for a Boolean function, namely majority. And Cook and Mertz took that framework to show that it works for all Boolean functions, by showing that it works for all polynomials. While this new algorithm applied to arbitrary tree evaluation instances, not just those computing modular plus and times, it came at a cost in the memory, which came because of the number of times it needed to access the programs adding and subtracting the input values. Where it was originally a constant number of accesses in Benor and Cleve and Berman et al., the new algorithm accessed an exponential number of times, which was exponential in the degree of the polynomial to be computed. Finally, in our new paper, we reduced the amount of recursion needed for arbitrary polynomials from exponential to linear. And while we pay slightly in the size of the field, the balancing ends up giving us an algorithm that takes log n, log n space to compute any tree evaluation instances, putting TEP a hair's breadth away from log space.
So, that's where we're at. The conjecture of Cook et al., at least as they originally stated it, is false. Now, it could still turn out that TEP is not in log space, and that something like this log-log factor is necessary. But at the very least, this should cause us to stop and reevaluate our belief that composition is one of those properties that's hard for space. Now, here's where I'd like to show some things about the proof, but unfortunately it's a complicated idea that gets technical very fast, and so I won't be able to show.
As promised, we're going to have registers RL, RR, and RU, each of which is log n individual registers over our ring. Our goal is to compute the value VU associated with the node U. Recursively, we'll assume that we have a program PL to add VL to RL, and program PR to add VR to RR. Now VU has log n components, but let's just focus on one of them. Each component has an easy polynomial expression of degree 2 log n. Just sum up over all the values of the inputs, which set it to 1. Thus, as long as we show how to compute any polynomial of degree d by a register program with order d recursive calls, we get a program running in time log n to the log n. Our space usage is log of the runtime, plus the 3 log n times log the ring size for the register memory. As long as our ring also has size order d, all of this is space log n times log n. Okay, let's show our program now. To start, we'll need what's called an mth primitive root of unity in our ring, which is a value omega such that omega to the m equals 1. These are basic objects with a bunch of nice properties and interpretations. But all we need is that summing omega over all its powers from 1 to m gives 0. An easy consequence is that summing omega to the jk for j1 to m also gives 0, as long as k isn't a multiple of m. If it is, then the sum is m, because each of these powers is 1. Okay, now we can state our key register program equation. For any n-variate polynomial q of degree d strictly less than m, and any two n-dimensional points, tau and v, 1 over m times the sum of j equals 1 to m of q evaluated on omega to the j tau plus v is just q evaluated on v. First, let's see why this is true. To make things easy, consider a polynomial q which is just the product of all the values, so n is exactly d. Doing the binomial expansion and grouping terms gives a sum of all k from 0 to d of all the parts with k tau variables and d minus k v variables. Rearranging the sums gives the same coefficient for each fixed k, namely the sum over j equals 1 to m of omega to the jk. Bringing back our equation for omega, plus the fact that d is strictly less than m, means that each coefficient is 0 except for the one where k is 0, for which we get m. Thus this whole sum reduces to the k equals 0 term, where we take no tau values and all the v values. To go from this to any polynomial, we just apply the same logic to each monomial separately, aka each product separately. So this gives us the full equation. Now to use this, for any j, we can easily set up our memory to be omega to the j times tau plus v. Just multiply r by omega to the j, and recursively add v. We can also undo this, recursively subtract v, and then divide r by omega to the j. In between, we add the evaluation of our polynomial q on our input registers to our output register. And doing this once for each j, the equation guarantees that we add exactly q evaluated on v to our output register, and the total amount of recursion is order m, since we make 2 recursive calls per pass. Lastly, in order to make m be order d, and to guarantee that we have mth roots of unity, we pick a ring of size roughly 2d and have m be the size of r minus 1, picking omega to be any generator of the multiplicative group.
To wrap up, I want to talk about some direct implications of our proof, and where things might go from here.
Our paper lists 2 other results that follow from our main theorem. The first is about the KRW conjecture we saw at the beginning, where before, the KRW conjecture implied that P separates P from NC1. Now with our new theorem, it would also imply that it separates L from NC1, a much sharper complexity result. Our second is about the permutation branching program model we saw briefly earlier. Our result implies that every function can be computed by a permutation branching program of exponential width and slightly superquadratic length.
Our biggest open question is to improve our subroutines, or, alternatively, show that you can't do any better than what we've got. Of course, the ultimate goal would be to get tree evaluation in log space by any means necessary, but using our method specifically would have a number of nice side benefits. This brings me to one last question. Can we use these ideas to prove bigger results in complexity theory as well? Right now, we have found a way to bypass what seems like a fundamental natural limitation of space. Namely, one block of memory can only be used for one purpose. Can we use this to attack some of the biggest questions in space-bounded complexity? Can we disprove the network-coded conjecture, which relies on information bottlenecks? Can we improve Savage's theorem and show that non-deterministic space can be simulated with a subquadratic overhead? Are we wrong, and L really does equal P? Okay, maybe that last part's a little bit overambitious. But in any case, it seems like just as good a time as any to reevaluate our long-standing beliefs about the weaknesses and strengths of space.